Potassium is going to react the most explosively because it's the biggest atom. Water is the oxidizer in this case. So water can strip an electron off potassium much easier than it can strip an electron off lithium. So potassium is much more reactive. But when the internet comes back on, I can show it to you. But right now, that's the way it is. This is different because these species want to lose electrons, whereas fluorine, chlorine, bromine, those want to gain electrons. So it's a different type of thing. So losing electrons bigger is easier. Gaining electrons smaller is better. And so size is going to have an impact there. And so we can see here, chlorine, bromine, iodine, what do these want to do? Gain electrons. So which one is the biggest? Which one's the smallest? Iodine's the biggest. So, is the biggest one the most aggressive as far as taking electrons go? No, it's going to be the smallest. So here we have iodine reacting with a reducing agent. And although there's a reaction there, it's mild. But here we have bromine and chlorine. Both of these are going to react with phosphorus, P4. So if we take bromine with phosphorus versus chlorine with phosphorus, can you tell which one's more violent? Yeah, chlorine looks more violent. In fact, it is much more violent. And that's because chlorine is smaller. It's taking electrons. So it's easier to take electrons from big species here than small species. And so we can get an idea of certain trends in chemical reactivity based on quantum mechanics. All right, so continuing this, a few more things to talk about. That is, let's take a look. Okay, after potassium comes what? Potassium had the electron configuration argon 4s1. And then we have calcium. Calcium is argon 4s2. It has 2 valence electrons, so calcium likes to form the 2+. After calcium, we have scandium. So can you do the electron configuration for scandium? Yeah. Argon 4s2. 3d1. Now, I've been telling you that the 3ds are core electrons, but what was common with all the 3ds that I've shown you up to now? They're full, and so the full sublevel adds some additional stability to it. This is partially full, and so if we were to rewrite this, we're going to rewrite this argon 3d1 4s2. Now the outermost, what are the outermost electrons? Because the outermost electrons are going to be the ones that are easiest to ionize, and that's going to be the 4s. That's 2 electrons there. And then an oxidizer comes in, well, it sees this. Now, if this were D10, that's a different story, but this is D1. And so, do you know scandium is a fixed charge cation? Do you know what the charge on scandium is? Scandium is a 3+. So an oxidizer comes in, takes off the valence electron here, +1. Oxidizer comes in, takes off the valence electrons, +2. Oxidizer comes in, we would think +2, and it should leave the 3D alone, but the 3D aren't so stable. And so it ends up taking all of them. And we end up with +3. Now once we get to titanium, titanium has these charges. It has +1, 2, 3, and what do you think the highest would be for titanium? Well, let's see. Well, let's take a look at the electron configuration. Titanium is argon 4s2, 3d2. And so if an oxidizer comes in, it's going to take the electrons furthest out. What are the electrons furthest out? The 4s. Therefore, we call those the valence electrons. And so in doing this, this is it. 3d2, 4s2. Titanium has technically 2 valence electrons. And these d electrons are in the core. And so +2 is a very common charge for titanium. And also those Ds, even though they're in inner shell, core electrons, those can be further attacked. Since it's not a full shell, subshell, excuse me, they can be attacked. And so if we lose one of these Ds, we'll get +3. If we lose both of these Ds, we'll get +4. And it turns out titanium-4 is very common charge, so oxidizers don't have too hard of a time taking all 4 electrons off. That leaves us with argon. Now, to start removing electrons from the argon core is going to be very difficult. So it's all filled shell and subshells. Okay, after titanium comes what? Vanadium. What do you think the charges for vanadium are? Okay, vanadium is argon, 4s2, 3d3. And so some common charges for vanadium are these. It's argon, 3d3, 4s2. We're going to put the outermost electrons out at the end. Oxidizer comes in. What electrons are going to be the easiest for the oxidizer to take? 4s2. So +2 is common for vanadium, and potentially +3, +4, and +5. We see all those charges in vanadium species. Okay. From vanadium comes what? After vanadium, we have chromium. Chromium, we get argon, 4s2, 3d4. Now I'm going to stop here for a second because I want to draw the orbital energy level diagram. Can you draw the orbital energy diagram for chromium? Let's see. And then you can compare it to the one